Welcome. This is a lecture 4 for module 1 where we are discussing tensors. So, in the last class we were basically discussed the tensor algebra. So, one of the important part of which is the we learned in the last class that tensor inner product of tensor, which is basically the so just to remember things, I just wanted to write it once again. So, A contraction B or the A inner product B, where A and B both are tensors. So, it is represented as trace of A transpose B. So, trace we know it is the sum of the diagonals of this product. So, A transpose B. So, both of these are second order tensors. So, now this is you see this is a contraction. What does this contraction means? This is sometimes we call as contraction. What does this contraction means? Now, see, this is both of them are second order tensor. So, this trace is a scalar function that we know, because if I write trace of a matrix which is or trace of a second order tensor. So, what is this is trace of A. AII. So, II is a summation implied in it. So, A11, A22 and A33. So, you see that inner product of two tensors is essentially a contraction, in a sense that tensor is a this has two direction, but trace does not has any direction. So, trace is a scalar. So, from a second order tensor it comes to a scalar. So, similarly, if I take the inner product of a fourth order tensor with the second order tensor, so it will give me another second order tensor. So, this is important, and this why I am discussing here. So, if you have seen the Hooke's law, right, the Hooke's law all of us have seen in this form, that sigma is C epsilon, right, where C is a constitutive matrix, right, and epsilon is a strain vector and sigma is a stress vector, right. So, these are in the void notation, right, which we have discussed in the last class. So, these are the vectors, but here these are the tensors. So, sigma is a second order tensor, epsilon is a second order tensor, but what is C? C is essentially the fourth order tensor. So, this fourth order tensor is essentially has 4 component. For instance, if I write it in component form, it has to be C I J K L. So, this we will discuss when we will discuss it in the material behavior. So, this is the elasticity tensor, or sometimes known as the Hookean tensor. So, this fourth order tensor is essentially, if I take the inner product with the with a second order tensor which is strain, then it will reduce 2 times. So, its dimension. So, from fourth order tensor to second order, it will operate on a second order tensor, and it will convert this to another second order tensor. So, this has to this probably we have not discussed in this last class. So, this we have to keep in mind. So, again we will see it in detail in when we will do it in the material behavior. Now, so in this lecture we will basically introduce the calculus of tensors. So, calculus is basically probably all of you have learned what is derivative, what is gradient of a vector field, what is divergence of a vector field. So, now we will concentrate on what is these quantities in a tensor field. So, I am using the word field, right. So, let us define what is field. So, values of tensor varies from point to point. That means, a field can be a displacement, a field can be a stress, right. So, if it is a displacement, as we know displacement is a vector, so we will call it a vector field, right. And if it is a tensor, for instance stress is a tensor field, second order tensor field. So, the values of these vector or tensors, or it could be a scalar field, for instance temperature. temperature could be different at different points. So, it is a scalar field. So, values of tensor field or values of this field varies from point to point. So, naturally, if it is a value, if it varies, it may varies or it may be constant also. So, if it varies from point to point, it will be a function of x, y and z, right. So, example, stress, strain of an elastic body varies from point to point. So, naturally, it is a function of x, y, z. So, tensor field or the zeroth order tensor, which is a scalar field, can be a function of a of x1, x2, x3, right. So, we write it in short form a of xi. So, if it is a vector field, then for instance, velocity, displacement or any other quantity, so which is also a function of x1, x2 and x3. Remember here that A has 3 component here when it is a vector, and all 3 components, that is A1, A2 and A3, are all dependent on x1, x2, x3. So, if I write it little in a expanded form, so A1 is or in a component form, A1 is also a function of x1, x2, x3, A2 is a function of x2, x1, x2 and x3, and similarly A3 is also a function of x1, x2, x3, right. So, this is the short form of this, and we write it ai xi. That means, ai's are all function of xi's, right. Similar to this, as a vector field, we can define tensor field also. The tensor field aij is essentially all component of the tensors is dependent on the spatial coordinate system or the x1, x2, x3 system. For instance, stress varies from point to point. So, x1, x2, x3 are all spatial coordinate system, right. Now, so once we know the concept of field, so a field could be scalar field, a field could be vector field, a field could be tensor field also. So, now the derivative of the field variable. So, once we know the field, so the field variable comes, right. So, the field variable, for instance, if I want to take the derivative of a scalar field, so it is dou xi of a, right. So, which I write it in short form a comma ix. So, this is important because we will be using this. So, when I write comma, that means a comma I, that means I am implying that del of xi of a, right. So, similarly, a I comma j, that means I am implying a I comma j, that means I am implying that del of del x j of a ith component. Remember, in the previous slide we have seen that ai's are all functions of x1, x2, x3. So, the ith component of vector A is differentiated with the jth component of the spatial coordinate system, right. So, these are the spatial variables, right. So, similarly, if I write it in this, if I expand it, it will form like this kind of thing. So, each component will be differentiated with respect to spatial system. Now, similarly, we can define a tensor. In case of a tensor, we can define. So, since tensor has 2 directional component, so when I write aij comma k, so this represent my del of xk aij. So, aijth component, which is also dependent on x1, x2, x3, is differentiated with the xk. So, this is important to remember here because we will be using more these shorthand notations, right. Now, I think all of you know what is derivative, but if I say it is a directional derivative, then probably you do not know. So, let us know what is directional derivative and why we need to know, more in this course we are introducing tensor. So, tensor are directional quantities, for instance stress, strain, these are the directional quantities. So, when I take derivative, the derivative could be along a direction, right. So, this motivators to learn what is directional derivative. Now, before going to a tensor directional derivative, let us understand what is if there is a scalar. So, phi is a scalar function of x, y, z, and s is a direction along which derivative need to find. So, this can be also done, right. So, if which is simply del psi, del x, del x, del s, and so on. So, parameterization of a curve, if we remember. So, any function which is x, y, z dependent can be taken derivative in this form, right. So, this I think all of you know, right. Now, let us learn what is directional derivative. So, a function y x here, whether I am not saying whether it is a scalar function, whether it is a tensor function, whether it is a vector function, I am not defining anything. So, let us write it in a simple form, what is directional derivative. The function y x is differentiable if there is a linear transformation d of y of x such that u approaches to 0. Now, where this u comes from? So, let us expand it y with the x plus u. So, if I write it in this form, if you have seen the basic differentiation formula, this is nothing but the basic differentiation formula, or you can obtain it from the Taylor series formula also. So, this thing, this quantity I am talking about is that linear transformation, which this d of y of x. So, it is a linear transformation on u. Now, this is the higher order terms which approaches to 0, right. Now, what does this means? Which approaches to 0 means that limit, so limit of u tends to infinite. So, this term if I divided with the norm of u, so this is essentially the norm, this quantity is known as the norm. For instance, Euclidean norm from a vector. So, it could be a distance. For a tensor, it could be a maximum norm, it could be a L2 norm, or the distance norm, or the Frobenius norm in case of a second order tensor. So, this this quantity should go to 0, but let us not bother about these things right now. So, let us see what this linear transformation means actually. So, this let us so now if this linear transformation exists and unique, then it is called simply derivative or Fréchet derivative. Probably you have heard this. So, Fréchet derivative of y at x0, right, and then this total quantity, this total quantity is known as the directional derivative or the Guitaut derivative, where there is a implied direction u is there. So, if you look these two expression carefully, this is a Fréchet derivative and this is a directional derivative. So, directional derivative actually operates on the Fréchet derivative. So, that means the directional derivative is computed by the action of the Fréchet derivative. So, we will see what this means. Now, the directional derivative exists, and if it is unique, then can be written as the usual derivative formula, where epsilon tends to 0, right. So, this this is the formal definition of the directional derivative. Now, let us see some example of how we use this. So, what we have learned? We have learned two things. One is Fréchet derivative and one is directional derivative. Now, let us see some example. Suppose we want to take the derivative of a function which is v dot v. V is a vector. So, it is a scalar function, dot product will lead to a scalar function. So, v dot v. So, what is the directional derivative if I want to compute the directional derivative? So, phi of v plus u is essentially v dot v to v dot u and order of how it comes, you just write, you just substitute in case of a v, you write v plus u and then multiply it. So, dot product we can just simply write it like this, v plus u dot v plus u, which will give me v dot v plus u dot v plus v dot u plus u dot u, right. Now, this v dot u and u dot v I can club together because all of these are scalar quantities. So, which I can club together and put like this to v dot u, and order of u is essentially u dot u. So, now if you compare the directional derivative formula, essentially directional derivative is this, right, and Fresher derivative is 2v, right. So, we can write it in component form also, right. Now, if there is a instead of a vector, if it is a tensor, right, tensor argument, right, phi of t, that means t is a second order tensor. So, if it is a t2, that means I can write it t into t, right. So, this if I want to find out the directional derivative, t plus u if I write, and the same way if I write. So, t u and u t, remember here. So, this is a second order tensor. So, this I cannot write t u equals to u t, because as we know we can think of second order tensor as a matrix. So, matrix multiplication is not commutative in general. So, that means a b not necessarily equals to b a. So, I have to write it in this form, t u plus u t. So, if I see in this, if I want to find out the directional derivative, so which is essentially t u plus u t. Now, suppose one of the popular function we are using or we know today is trace of t. Now, trace is a linear function if you look carefully. So, I think I have also discussed this, trace is a linear function. So, trace of t plus u, which is essentially trace of t plus trace of u, right. So, now, if we see the directional derivative, so which will be essentially trace of u. So, trace of u I can write that I contraction u or I inner product u, because I inner product u is essentially trace of I transpose u. So, I transpose is essentially I, and I multiplied by u is essentially u, right. So, I can write it in this form. So, now determinant of t, determinant is the third invariant of a trace tensor or strength tensor, we know this. So, determinant, if we want to take the find out the directional derivative and along the direction of u. So, this contrary to the trace, determinant is a nonlinear function which cannot be just write det of t plus det of u. So, if I expand this determinant of t plus u, then det of t, cofactor of t, inner product with u, and t cofactor inner product with cofactor of u, and then det of u, right. So, these two quantities goes into the order of u, and then this could be the this is the my directional derivative. So, d of phi of t along the direction u. See, whenever we use tensor arguments, our direction has to be the tensor directions. For instance, in case of a vector, we always use a direction as a vector, but here in case of a tensor, it is always has to be the in the direction of a tensor. Now, those probably who do not know the what is cofactor of t, it is the adjoint transpose which we have from our matrix algebra knowledge, we can find it. So, the inverse of a tensor I can define it in like this, cofactor transpose cofactor of that tensor transpose divided by det of t, determinant of t. So, in a matrix algebra, we have seen this and we will just note it little. So, this is tensor inverse. Actually, if A is if I had to take inverse, so which from the matrix algebra knowledge we can write cofactor of A divided by the det of A. Now, A cofactor or the cofactor of A, which is essentially the cofactor matrix or the adjoint matrix, right. So, let us see how this cofactor matrix is computed. So, if A is A11, A12 and so on, then adjoint matrix is a Cij. Now, what is Cij? Cij is a this quantity which is essentially the determinant of the minors. So, Mij is from deleting ith row and jth column. For instance, M11. So, M11 is essentially this, right. So, this portion. So, determinant of M11 is A22 A33 minus A23 into A32. So, C11 is minus 1 1 plus 1, that is minus 1 to the power 2, that is 1, which is A22 minus A33 minus A23 into A32. So, C11 like this we can find out the C11 and then other quantities. So, this is very well known from the matrix algebra. Now, this is actually is the adjoint matrix. So, this forms the transpose of this actually is the adjoint matrix, and which is essentially known as the cofactor matrix. So, in our previous case, where we actually found out the directional derivative of determinant of tensor T, which I have expressed, you can actually verify these things, whether the determinant of summation of two matrix can be written in this form. So, this is very helpful to find out the directional derivative. Actually, one can prove this is the determinant of the total determinant. If you sum these matrix and then take the determinant and then instead of that has to be equal to determinant of the individual matrix, cofactor of T inner product of U and then so on. So, cofactor of T inner product of U is essentially trace of cofactor T transpose into U. So, this is essentially a scalar. So, this is also a scalar. So, this becomes a scalar. So, finally, the determinant will be a scalar. Even though it is a scalar function, these quantities makes them the nonlinear function. So, it is not just simply det of T plus det of U. This one can remember. Now, another interesting thing probably all of you have seen is the nabla operator or del operator. Del operator is a vector actually. So, del del x E1, del del y E2, del del z E3 and so on. So, what we write is essentially del I E I. So, in a indicial notation. So, gradient of a scalar function. So, when I write gradient of a scalar function, it is just del of psi. So, del of psi means each component has to be taken, the derivative has to be taken with respect to each component. So, del of psi x, del of psi E1, these E1, E2 and E3 are the unit vectors along the Cartesian component direction. Now, this quantity is a vector quantity, right. So, scalar even though psi is a scalar function, the gradient of this scalar function is a vector quantity. So, this has to be remembered. Now, another the general formula for finding out gradient is essentially the inner product with this inner product with a vector u which is a direction here. So, it is essentially the if you take the inner product and with the del operator of this function with the u, and then these two quantities is equal actually. This is how gradient is defined. So, with appropriate product inner product. So, why the appropriate product inner product, the word appropriate inner product, because u could be a vector, u could be a tensor, or x could be a vector, x could be a tensor. So that is why in case of an inner product defined on a vector field, which is essentially dot product, in case of a tensor product, which is essentially the inner product of two tensor, which is again a scalar. So when defining the gradient, the proper inner product has to be defined. Now this could be, those who are interested, this could be elaborated much more and study further on this aspect. So now our objective is to find out the scalar product, a scalar function here. Now if I write from our previous knowledge of directional derivative, if phi of x is a scalar function with a vector argument, that means for instance the function we have seen v dot v, both of these are vectors, but their dot product is scalar. So such kind of function, so if I want to write in the sum with another vector u, so which is essentially phi of x plus u, phi of x and del phi of x and u. So from our definition, this del phi of x dot u, which is essentially I have represented with a braces here, essentially to define the inner product. So this del phi of x u is essentially the del d phi of u. So it is equal to the directional derivative. Now this this quantity is essentially del phi of x dot of u, right. So inner product defined. So if I write this thing and then if I write it in component form, so my directional derivative my gradient, I can find out gradient of a vector field very easily, which is essentially the component form del of phi xi, which is del phi of xi, del phi of x with xi. Now how can I find out here? This is essentially if I take ui as ei, because ei's are the unit vectors along the x direction, y direction and z direction. Now similar to this, if we find out scalar function with a tensor argument, the same way we can find out the gradient. So but the function is tensor function, but the arguments are the scalar arguments are tensor. For instance, the trace is a scalar function, which is a but the argument is tensor, trace of a second order tensor. So if I now want to write the gradient, so I can write it del phi of xij with del phi of del x. See, this is a tensor, so derivative with respect to tensor function. So contraction u. So if I write it in this form, so in the initial form it will look like this. So gradient of a tensor scalar function with tensor argument in a component form is this essentially. See, phi is here is a scalar function, this has to be remembered. Now similarly I can expand it for a tensor function, where I can just simply write it in this form with the proper inner product defined. Now for instance, if I see, I was talking about the trace is the first invariant. If I want to find out the gradient of I1 with respect to sigma, then this formula tells me that it is I. So this sometimes we will use this kind of treatment for finding out the required derived quantities in this course. So now another important thing is a vector function. So gradient of a vector field. So gradient of a vector field, even though inner product is defined, this quantity is not an scalar quantity. So this is a vector quantity. So if I write it, the gradient of a vector field in a component form, this will look like this. So the definition of a gradient of a vector field is this. It is essentially equals to the directional derivative. So del of v of x is a gradient of the vector field, so which is essentially in a component form del vi del xj ei tensor product ej. Now remember, this is a expansion, that means this is a matrix. So, gradient of a vector field is a matrix. So, this has to be remembered in mind. So, gradient actually increases the number of direction. So, it was a vector field. So, now it becomes a gradient of that vector field becomes tensor field. So, it has two component I j. Now, another important quantity probably all of us know, divergence. How the divergence is defined? So, we know that del dot V is the divergence of V, right. So, which is essentially I can write trace of the gradient, trace of the gradient. So, if I write it in this form or the from this component form, so del V I del of x j is essentially trace of E I E j. So, trace of E I E j I can write it is as simply dot product. So, this proof is very nice actually, E dot E I E j, and then it becomes the del I j and then del V I del x j. So, this is known as the divergence of a vector field. So, now another quantity probably all of us want to know, that divergence of a tensor field. So, divergence of a tensor field similarly increases another directional level, which is becomes a third order tensor. So, these are the general formula, and actually we can define for it for any order of tensor. So, this becomes a third order tensor. Now, similarly divergence sorry, this is a gradient of a tensor field, and the divergence of a tensor field also becomes a is defined like this, del dot t dot v. So, del dot t transpose v. You see, if this is a second order tensor, this quantity becomes vector and this quantity becomes dot product. So, now this in a component form I can write it in this form. Now, the next we will see some example on this. So, gradient of a vector which is simple, we know that V I E I dot V j E j and then V j comma I is essentially we have seen this. So, another important thing is Laplacian. Laplacian is essentially del dot del. So, del of V. For instance, if I can write it in this form, that del dot del f, right. So, in this form I can write. So, the del f becomes the vector, and then it's again it's a dot product with that. So, it becomes a scalar, right. So, now curl of a vector field. So, all these things you know, because curl is a cross product. So, if I write it in component form, it will look like this. See, we have used here the Christoffel symbols. So, this becomes this. So, curl of a vector field is a vector. So, Laplacian of a vector field. So, Laplacian is again I can write it in this form, del dot del of u or v, whatever it is. So, if I write it in this form, so del I, then Laplacian of a vector field will be a vector. So, these things we know already from our knowledge of vector algebra, vector calculus. Now, there are some important results, these also we need to know. So, del dot del cross V, which is essentially 0, and del of psi of phi is phi of del of phi and plus del of psi of phi. So, and then del dot del of psi is essentially del square psi. So, psi is a scalar function. So, this is essentially the Laplacian. So, now this we will go for an example today to see what these quantities looks like. Now, for instance, if I define a scalar field of this and vector field of this, then what does this del phi means? So, del phi is essentially this del operator or the nabla operator, then x square minus y square. If I take it, if I take inside it, it is just the derivative with respect to x and just the derivative with respect to y. Since it is not a function of z, then this quantity is gone 0. So, now del square phi, that means the Laplacian of that scalar function. So, essentially del phi dot del or the del dot del phi. So, del phi actually we have computed from the previous part, and then if I just take again take it inside, so it becomes this. So, it is a dot product. Okay. So, now divergence of that u vector, this is a vector. So, divergence of u, again this is a dot product. So, this is essentially a scalar. So, now if you see this all those quantities here are scalar, but it is not necessary that all these quantities will be scalar, right. So, for instance, the gradient as I have told that this is a vector, this will increase the dimension of the vector, dimension of the field variable. That means, if I do take a gradient of a vector field, it will become a second order tensor. So, if I just take component wise, take the derivative, it will look like this, right. So, curl is again is a vector. So, if I take the determinant of this, so the determinant in that cross product we have defined earlier, cross product. So, it becomes this. So, it is a vector. So, this essentially completes our tensor algebra. In the next class, we will review some of the integral integral theorems, which will be useful when we will be doing for the boundary value problem. So, the next class will go for the integral theorems. Thank you.